Hello everybody, welcome back to Geometry in Chapter 5. Today we will be talking about angle bisectors, and also there's a theorem for that too, the angle bisector theorem. So you'll probably notice that my orientation is changed this time so that it's vertical, because I think it might be helpful if we actually saw the entire screen for some of this stuff instead of like just half of it on the horizontal. So let's try it out, let's see how it goes, right? Something a little bit different. Speaking a little bit something different, you'll notice on the right hand side I have a totally irrelevant picture, but I figure, you might get a good laugh if you still remember how unions and intersection actually works out. All right, so here we go. So for this section, what I want to do is I want to define what is an angle bisector. Okay, I want to define what is an angle bisector. So, just going by the name of it, then that means that I'm taking an angle and I'm cutting it in half because of bisecting. So here is our formal definition, which we can see on the bottom over here, okay? So if we have point D, right, if point D is in the interior of angle ABC, and ABD is congruent to DBC, or you can say that the measurement of those angles are congruent or equal to each other, then BD is the bisector of ABC. So here is the picture that's on the right hand side. So first of all, I'm going to go ahead and create that BD, the ray then. Okay, so here is BD, the ray. And here's what the definition is actually saying. D, which you can see is in the interior, so the first part is satisfied. The second part is that these two angles right here, ABD, has to be congruent to this angle right here, DBC. And if those two cases are true, right, one is in the interior, and then you have those two angles are congruent to each other, then we can say that BD is going to be our angle bisector of BC then. So hopefully that's pretty straightforward. Now that we know how the angle bisector work, let's look at what is known as the angle bisector theorem. So this one is a little strange because it's one of those theorems that shows something called existence and uniqueness, which I will explain in just a little bit. So here it is, Theorem 5.3, the angle bisector theorem. We are saying that every angle has one and only one angle bisector. Every angle has one and only one angle bisector. Well, you're probably thinking to yourself, well, duh, because we can kind of clearly see that there's only one bisector for each one of these, just like how there was only one midpoint for every segment. Well, unfortunately for geometry, we need to actually prove all of this stuff then, because hey, what if somebody comes along and say there could be two angle bisectors or maybe three angle bisectors? Well, let's just see how this actually works out then. Earlier, I was saying that there is something called, this is what is known as an existence and a uniqueness proof. So here's how that works then. The idea of existence is that, hey, I need to show that there is at least one, right? So in the part of the theorem which says that every angle has one, that means I'm showing that, hey, it's there, it's somewhere there, right? Could be one, could be two, could be five, could be more, at least one is there. Then the word only one basically is what is showing uniqueness, meaning that there is exactly one of these angle bisectors and no more then, okay? So the first part showing existence, meaning that the angle bisector is there. The second part, the uniqueness, is saying that there is only one of those angle bisector then, okay? So then that means that this has to be broken down into two-part proof. We have to show the existence and then we have to show the uniqueness. So here it is. Let's go ahead and go through it. So what I'm going to do is I actually wrote the proof for you on the right hand side, and I'm going to go ahead and draw in the illustration as we go along, so then that way you can see how it actually works out. So first, what I'm going to do is I'm going to go ahead and look at the first part, which says choose point A and point C such that AB is equal to CB. And this is on the point plotting theorem. And I should be a little bit more specific, because what I'm going to do is I'm going to choose point A on one of the sides over here. So this is going to be A over here. And then I'm going to choose another point C, which is going to be on the other side for the angle, but I want to choose it at a specific location such that AB is equal to CB. So then that means that C is approximately right here, because you can kind of see that if I swing this downward to create kind of like a radius, then those two sides are going to be congruent to each other. So that's going to be my first part of the proof, okay? So let me go ahead and kind of erase those little small pieces right here. Okay. Now let's go to the second part. Next, what I want to do is create AC. Okay. And I can do that because I know of the line postulate back in chapter 1, right? It was a long time ago. This allows me to basically just create a line segment that goes from A to C, like this. Okay. Next, step 3 says there exists a point D on AC such that D is the midpoint of AC. Well, that is the midpoint theorem, not the definition of midpoint, because once again, definition says that it breaks it into 2 equal parts. This one is a uniqueness theorem, if you kind of remember, because this is basically what we're trying to prove, right? I'm trying to show that there's only one bisector, whereas this theorem, the midpoint theorem, says that there's only one midpoint. So over here, right in the middle, I'm going to go ahead and point my point D right there. And because D is the midpoint, I can go a little bit further, right? I can probably say that these two guys are going to be congruent to each other. Next, afterwards, as of right now, we are located right here. We looked at part 3, and then we did the midpoint theorem. Next, we're going to go ahead and create BD, the ray. And even though I'm creating a ray, this is still considered a line postulate because a ray is a subset of a line. So here, I'm going to go ahead and create BD like so, just like I created AC using the line postulate. Both of them will be the same reason. There's no such thing as a ray postulate. There's no such thing as a segment postulate, just a line postulate to cover them all. Hey, look at the 2 triangles that I just created right there, right? You'll probably notice that, yeah, they are definitely congruent to each other because of SSS. And here, from step 4 to step 5, you can probably guess it. Yeah, I skipped a few steps and cheated. But the idea is there, though, nonetheless. Triangle ABD is congruent to triangle CBD by SSS. And now, those 2 triangles are congruent to each other, then I can say their corresponding parts are going to be congruent. And the corresponding part that I want specifically, oh no, I just erased it all, so hopefully I can put it all back. Triangle ABD is going to be congruent to triangle CBD. Yes, okay, good. Saved. Whew. What I need to do is I need to go to my next step, which is say angle ABD is congruent to angle CBD. And in terms of where that's located, hey, that's looking at this angle is going to be congruent to this angle. And if you notice what I'm doing right now is I'm basically trying to build into my definition of angle bisector. I need to show that these 2 guys are congruent to each other to say that that the BD is going to be my angle bisector. So in this case, I did that, right? So that's going to be my part 6 right here. By corresponding part, those 2 angles are congruent. And then now, therefore, BD is the angle bisector of angle B, definition of angle bisector. And we can clearly see that D is in the interior, so we don't have to worry about that discrepancy in the picture. So there's the existence proof. We showed that the angle bisector is there. Now what I want to do is I want to prove that that angle bisector is unique, meaning that that's the only one. Well, the unique theorem, uniqueness part of the theorem, you're going to have to do a little bit something trickier, and that's where we have to use the idea of indirect proof. So indirect proof basically means that, again, if your proof is something like, say, A implies B, then your indirect proof is going to do the following. You're going to assume the negation of what you're trying to prove. And so what will happen then is that according to modus tonin again, the result is that you're going to get the negation of A. So what that means is we're going to go ahead and assume the negation of what we're trying to prove. And somewhere along the line, you're going to see that something doesn't make sense because it's the opposite of something that is given to us. Basically, there's going to be some sort of contradiction. So let me kind of show you how this works then, okay? So let's go ahead and write that out. Assume that there are 2 angle bisectors, okay? Assume that there are 2 angle bisectors. So you can kind of see in my picture, that's exactly what I've drawn. So here you can see one angle bisector and then the other angle bisector, even though they don't technically look like it, okay? Here's what I'm going to do then. I'm not going to write out the entire proof because that's going to be a little bit too lengthy. Let's do this. Since there are 2 angle bisectors, then that means that I can choose some points on the angle bisector. Let me first form AC just like I did in the previous proof. And then in that line segment AC by the line postulate, I'm going to go ahead and say that the intersection to the first angle bisector, we'll go ahead and call that D. And then the intersection to the other angle bisector, we'll go ahead and call it F. So in this case, then that means that I'm basically saying that BD is the angle bisector, right? BD is the angle bisector. And then also, BF is going to be my angle bisector. And what I want to do is I want to show that this is not right. This is something funky about this. There's something strange that doesn't quite work. Well, let's see. Let me go ahead and see if I can draw out what we have. So let me just draw this triangle over here. Let's say we have triangle ABC, and then we're going to go ahead and use that D over here, right? Disregard BF for the time being. Let's just see what happened there. I'm going to go ahead and create BD so you can see two triangles. Hint, hint. You can probably guess that I'm going to try to show congruency in triangle in this case. Let's see. My assumption is that just like in the previous proof, I am going to say that AB is congruent to BC because I could choose 2 points wherever they are on the line using the point plot postulate. I know that BD is going to be an angle bisector because that's what I assume. So that means that these two are going to be congruent to each other. And hey, that means BD is congruent to itself. So that means by SAS, these two triangles are going to be congruent then. So SAS, that's good. And that will then allow me to say that AD is congruent to DC. Okay. Next, I'm going to go ahead and do the same thing, but with triangle ABC, and I'm looking at point F this time. Okay. So here's point F. Here's triangle ABC, right? Let's see if the same setup is going to work out. Again, AB is congruent to BC because of what I assumed to begin with. We know that BF is the angle bisector because I said it over here. So that means that this angle is congruent to this angle. And once again, BF is going to be congruent to itself. So that means by SAS, these two triangles are congruent to each other. So what that means is AF is going to be congruent to FC. Now, if you're wondering, well, where's the contradiction in that proof? Well, here, look at my picture once again, right? Notice that the way that I wrote it, I have D is in between, I have it so that D and F are in between A and C, the segment, right? D and F are just somewhere in between. According to this first one, D has to be the midpoint because AD is equal to DC. According to this one over here, F has to be the midpoint because AF is equal to FC. Well, if D is the midpoint over here and F is the midpoint over here, that right there is a contradiction because remember what the midpoint theorem says? There can only be one midpoint. So right there, that's the part that's not going to make sense because there's a contradiction somewhere along the way. So that is my uniqueness proof. My assumption cannot work, which is the negation of what I'm trying to prove, because the contradiction is that it contradicts the midpoint theorem or the midpoint theorem. All right. Well, fortunately, you guys won't have to do these kind of existence and uniqueness proof for another 2 or 3 chapters. So this is just kind of like an introduction. So let's look at this last part right here, which is an example of the angle bisector in action then. So here in this picture, let me not scroll all the way down yet. I'm going to give you that triangle ABC is going to be congruent to triangle ABE. So this, first of all, be very careful. This is a 3-dimensional picture. So that means that we're looking at this as a 3D. Okay, so you can see that perforated line underneath for EB and DB. That means it's kind of like in on the backside of this pyramid thing. So triangle ABC, so that's going to be this guy right here, right? Is congruent to the triangle ABE. So that means it's kind of like the backside over here. That triangle is going to be congruent. Okay. D is the midpoint of, let's see, D is the midpoint of EC. And what I want to do is I want to prove that AD is going to bisect EAC. So I think unfortunately, because I kind of drew all over the triangle, it's a little bit hard to see. But let's focus on the triangle that actually matter, which is that face triangle over here, which has A, which has E, which has D, and which has C. Now, in this picture, what I need to do is I need to prove that AD is going to bisect EAC because that's what I need to prove. So these guys right here You're probably going to put the question mark because I want to prove congruency over there, right? Let's see, in terms of what's given, we know that this is going to be congruent to this because D is the midpoint of EC. And I know that these two triangles are going to have this guy right here congruent to itself because that's shared. Now, if I know angle ADE is congruent to angle ADC, that'll be great because I have SAS, but unfortunately I do not. What I don't have yet, or what I haven't used, is that the triangle ABC is congruent to triangle ABE. So those are the two side triangles right there. So a little bit hard to see, but if you can kind of pull it out, you can see that AC right here, right? And let me just kind of highlight it so you can see it a little bit better. If those two triangles on the side of the face of this pyramid are congruent to each other, then this side, AB, should be congruent to AE, the side over here, right? So there it is. So that's going to be my last sneaky part. And that means that these two triangles that I'm trying to show that are congruent will be by SSS. And then by corresponding parts, then we can say that we can have those two top angles congruent, and as a result, proving that, say the definition of angle bisector, those two angles are congruent to each other then. All right, so here it is. First, we're gonna go ahead and do SSS like we said. Those two triangles on the sides are congruent to each other, so that part is given. Next, we're gonna go ahead and say that AE is equal to AC because of corresponding parts. So right there, we basically nailed this part and nailed this part right here. Next, we're going to go look for another side. Next, we're going to go ahead and say that D is the midpoint of EC, and that one's given. And from there, ED is going to be equal to DC because of the definition of midpoint. Now we have two of the sides of our triangles to be congruent. Two pairs of the sides of the triangles to be congruent. Finally, AD is congruent to itself by the reflexive property. So once again, the two triangles are congruent to each other, but this time by SSS. And then now we can say that those two top angles, EAD is congruent to CAD by corresponding parts of congruent triangles are congruent, CPCTC. And then finally, AD is going to be the angle bisector of EAC because of our definition of angle bisector, okay? And again, all of these proof, we don't really care or have to say that D is in the interior because it's already shown in the picture. It's kind of like one of those things that will be trivial. All right, thank you so much for watching, and hopefully